sign in again. All right. So yeah, eigenvalues and eigenvectors are very important, and we are going to use those in 17C a lot. So that's one of the classes I'm also teaching this quarter. So there's a whole chapter on that where it's all focused on eigenvalues and eigenvectors and how they can help us solve some interesting questions. So this is sort of a preview. You will be expected to know, we still review it in 17C, you know, what we're learning right now, but at least you will be familiar with this idea. All right, so it's kind of based on, we got to kind of set this up so you can see what's unique about an eigenvalue and an eigenvector. When you multiply a matrix by a vector, and one big note here, I've always thought this is a little strange. We've been writing our vectors as a row matrix, right? Where it's just one row, two columns, like the vector 1, 2. Well, in truth, that's just our choice of representing a vector. We could represent it that way, but we could also represent it as a column vector, and just knowing that this means the same thing, okay? Because we kind of need that, because if we think about multiplying a 2 by 2, if I were to write it like this, that would be a 1 by 2, and I wouldn't be able to multiply it. But now that I've made it a column vector, it's a 2 by 2 times a 2 by 1, which of course will be generate a 2 by 1, which means when we multiply at least a 2 by 2 matrix by a 2 by 1 vector, we're going to get another 2 by 1 matrix, which we could interpret as another vector. Okay, so we can think of this as a matrix A times some vector is going to give us another vector. Let's call it W. Okay. And let's see what that vector is. And so we can multiply this out. 1 times 1 is 1, plus 3 times 2 is 6. That adds up to 7. And then this gives me 2 minus 2 gives me 0. And the question then is, what happens when I multiply this vector v? So let's plot. I left some axes here. The vector v, 1, 2, I could denote that. I'm not going to draw the little hash marks, but you can just imagine that means go over 1, up 2. So that vector v might look something like this. There's vector v. And when we ended up multiplying v times this matrix, we ended up getting a completely different vector, right? 7, 0 is a vector. So yeah, this is x, this is y now. So that's a vector that's 7 units in the x direction, and you don't go up at all. So try to do this in green. So we could call this vector W, but you know, what is W? That's what we got when we multiplied matrix A times our vector V. And so one takeaway, albeit not very interesting, we'll get to that in a minute, is when you multiply, in this case, when you multiply this vector by this matrix, it had the effect, if we think about it, how did it change this vector, right? It's a completely different vector. So, but how would I describe the change? Well, I could say that it definitely changed the direction, right? It's now pointing in a different direction. And, you know, hopefully you can see here that the magnitude is also different. Remember how to find the magnitude. So if I wanted to find the magnitude of vector v, the length of it, that's just the square root of each part squared. So that ends up being √5 for v. Whereas this vector here, I don't really need a formula. I can tell that that's 7 units long, right? Because it's 7, 0. So clearly it changed both the magnitude and the direction of vector v. Magnitude is the same as length, yes. magnitude or the length. So, and that's I just made a note here. That's usually what happens. If you multiply some random matrix by this vector, you're going to get another vector, and there's usually really nothing really in common. It's just a completely different vector that changes the magnitude and the direction. But then I made a note here, there are a few exceptions, of course. Let's try this next example. I have this matrix here, 0, -1, 1, 0. That's matrix A times a different vector here, V. Let's see what we get here. So I get 0, -3 for my top entry, 3, 0 for my bottom entry. So I get another vector. Once again, we can call this W if we want to. But what's the connection here? Well, vector V, 3, 3, is a vector over 3, up 3. So that's a vector like this. Here's vector V. And you could say, you can kind of tell here that, if this was 3 and this was 3, this makes an angle of 45 degrees, right, with the x-axis. And when I multiplied it by this matrix, I get the vector -3, +3, -3, +3. So this is W, but I really want to emphasize that's what you get when you multiply the matrix times V. And so how would we describe this one? Well, hopefully you can tell without actually working it out, just based on the triangle, the length of W is exactly the same as V. So it did not change the magnitude or the length, but it did, you could argue then, what did it do? It kind of rotated. You could say, one way to describe it is you could say it rotated this vector V by how much? Because remember this angle here would also be 45 degrees. So what would that be? That would be 90 degrees, huh? Because this is 45, that's 45. So we could say that A times V had the effect of rotating V, I guess, do you know what CCW, counterclockwise? That was my shorthand notation. CCW. Counterclockwise by 90 degrees, but preserving, meaning the magnitude stayed the same. It was preserved. Okay, so that's kind of interesting. Yeah, it gave us a new vector, but at least it didn't change the magnitude, right? All it did was change the direction. Let's try one more here. We'll try this one on your own. So multiply this matrix by this vector, see what you get, and then see how would you describe what's happening, I guess. So I'm getting it's root 2 over 2. You might recognize these, right? That sounds like a trig value, huh, for an angle. And there is something called a rotation matrix, which is what's happening on this one, and we'll see on this one as well. That's not really that important, but it's important to know the idea that a matrix can just rotate a vector. So this is 1 root 2 over 2 minus 1 root 2 over 2. So that's going to be 0. And then I'm going to get root 2 over 2 plus another root 2 over 2, which means I have two root 2 over 2's, which is just root 2. And if we think about what's going on here, 1, 1 is an easy vector to sketch. Once again, at an angle of 45 degrees. And note that the magnitude of vector v is the square root of 1 squared plus 1 squared, which is root 2. So that's the length of v. And when I rotated v by, I'm sorry, when I multiplied v by this matrix, I got the vector 0 root 2, which is pointing straight up. So this is W A times V. And notice this length right here is root 2, which means once again, the magnitude was preserved, but this thing got rotated. You could argue this is rotated counterclockwise by 45 degrees. So that's probably how I would describe what's happening here. So there's some of the book problems you'll see on the suggested problems to do say, describe what happens when you multiply this matrix by a vector. That's what the things that they're getting at. When he says, describe what happens, like, is it rotated? Is the length the same? That's what they're getting at. So we could say A V rotates V counterclockwise by 45 degrees. That's probably good enough. So to summarize what we've learned so far in these three examples, go back to number 1. Generally speaking, when you multiply a matrix by a vector, you get a completely different vector in a different direction and a totally different length. That's what usually happens. In some special cases, when you multiply a matrix times a vector, you get just a rotation of the vector with the magnitude staying the same. So what would be the third option? What would be a third kind of, well, I guess third option, but the second kind of cool thing besides rotating a matrix? Is it possible that I could have a matrix so that when I multiply it by a vector, it only changes the magnitude? So it doesn't rotate it, but just changes the magnitude. Okay. And you probably could realize, yeah, the answer must be yes, right? There should be, right? Kind of, if all those other things can happen, there should be some situation where this can happen. So this is what you talked about today. So let me give you my take on this. So if I had this matrix A and this vector V, let's see what happens when we multiply them together. So I do 3, 6, -1, -4 times -6, 1. Gives me -18 plus 6 is -12. 6 minus 4 is +2. So I get another vector as expected, but notice that -12, 2, if I factor out a 2, remember you can just like you can multiply a constant into a matrix or a vector, you can factor it out too. That just is double my original vector, right? So we had A times V gave us this new vector, but we realized that's just twice my original vector. It's pointing in the same direction, just twice as long. So like, for example, since I drew graphs for the other ones, let me draw one right up here. We can see this up here. So if -6, 1, that goes the other way. Bummer. I know what I could do. We could pretend, see, I can't erase in pen. We could pretend that I didn't actually draw that. Let's say I drew my y-axis right here, and this was my negative x-axis. So negative 6, 1 might be a vector that's negative 6, 1. Let's say that's right here. Here's vector V. And when I multiplied it by matrix A, what I got was 2V, which you could, that's just basically doubling the length of this vector, right? It's like tagging on another V on top of that. So the green here is A times V, and I can see that that's just double my vector. So it's not changing the direction, it's just affecting the magnitude. You can think of it as stretching it out. Okay, so let's see, let's go down here. So A times V is equal to 2 times V in this case. Which means we can think of that as stretching out vector V by a factor of 2. And when this situation happens, it turns out this is the one we're really interested in. This is the situation that's going to have lots of uses for us going forward, both in the end of this class and also in 17C. When this happens, the vector V, so this doesn't work just for any old vector. If I took vector matrix A times some different vector, that's not necessarily going to happen. So it's a property of both the vector itself, and we call that an eigenvector. It's an eigenvector. It's a property of the matrix. It comes from this. It's a special vector. We'll talk about how to find that. And the stretching factor, this 2 here in this case, is called an eigenvalue of A. And you've already probably seen this. We usually use lambda to describe that. So lambda is equal to 2. That's an eigenvalue. And so then, since I told you we're interested in these things, the natural question would be, are there more eigenvalues and / eigenvectors for this particular matrix A, right? And how do we find them? The answer to the first question is yes. So for things that we're interested in, I'm going to put generally speaking, if you have a 2 by 2 matrix, you should have 2 eigenvalues. Each one has its corresponding eigenvectors. 2e, sometimes I get tired of writing 2 eigenvectors. If you have a 3 by 3 matrix, you'll usually will have 3 lambdas and 3 corresponding e vectors, etc. Okay. There are some in the book that have 3 by 3 matrices where you have to find all 3 lambdas and the corresponding eigenvectors, but we are going to spend 95% of our attention on these, on the 2 by 2 matrices. So you should expect 2 eigenvalues and 2 corresponding eigenvectors for every 2 by 2 matrix. So we've answered the yes, are there more? Now, how do we find them? Here's the deal. In the interest of time, because I really want to go show some examples of this process, you should have seen this in class, or at least in one of the recorded videos that Dr. Burke put out of the why. Where does this come from? Because that is an important discussion, but it takes a little bit of time. I do have some notes on that on my website if anybody's interested. But I'm going to go straight to the process without any explanation here, because it's such an important thing that you should know how to do right away here. So, okay, so here's how we find it. Here's our matrix A. And what you saw in class, right, to find my eigenvalues, we are going to try to solve, we want to set, so to find my lambdas, we are going to do the determinant of our matrix A minus lambda times the identity matrix and set that equal to 0. Okay, again, there's a whole long there's a lot of stuff in between here to get to here, right, that I'm cutting out here. And what does that mean, the determinant of A minus lambda I? Well, if I took A, 3, 6, -1, -4, minus lambda times the matrix I, which is an identity matrix, 1, 0, 0, 1, you can distribute, right? This is a constant, so I can distribute the lambda into everybody. So I get 3, 6, -1, -4, minus lambda times 1 is lambda. Lambda times 0 is 0, 0, and another lambda. And remember, the way we add or subtract matrices, you have to add them by, like, you know, the position. So what it boils down to, I'm going to have a 3 minus a lambda in this spot. 6 minus 0, that's going to stay as 6. -1 minus 0 is going to stay as -1, but then I'm going to have -4 minus lambda. And I want to set that determinant equal to 0. And actually, from here on forward, we're going to cut this even shorter. If we want to find our eigenvalues, what's going to always end up happening, if you do this and then this, is what's going to essentially happen is you're going to get this same matrix with a minus lambda there and a minus lambda there, right? Minus on your main diagonal entries, there's just going to be a minus lambda and minus lambda. And then you're going to take the determinant of this matrix and set it equal to 0. The determinant is just the product here times this. So I have 3 minus lambda, -4 minus lambda, minus the product of the off diagonal, which is 6 times -1. So that's minus -6. Set that equal to 0. Yep. Yeah, identity, at least for a 2x2. If I was doing a 3x3, which there are some in the book, but I don't think she assigned any, and I don't know, it's not really that important. We're not going to ever use the 3x3s. But if this was a 3x3, then I'd have the identity 1, 0, 0, 0, 1. You know, I'd have a 3x3 identity matrix. But for what we're going to do, it should always be this. Now, what ends up happening? You can probably see, if I were to FOIL this all out, I'm going to end up with a lambda squared, which is a quadratic. And so you're going to end up having to factor most of the time, or possibly use the quadratic formula. So to speed up the process, what I usually do is I multiply it out backwards. You're probably used to starting here and doing this. So I actually start with negative lambda times negative lambda gives me lambda squared. Negative lambda times positive 3 is minus 3 lambda. This is plus 4 lambda. 3 times -4 is minus 12. And then this gives me plus 6. And then it's kind of already set up. I just have to combine a couple of terms. Lambda squared plus lambda, -12 plus 6 is minus 6 equals 0. And I can factor that fairly easily. Lambda plus 3, lambda minus 2. So my two eigenvalues are, and what we usually do is it doesn't matter which one you call which, but there's two eigenvalues, -3 and positive 2. So we're just going to randomly, let's just decide lambda 1 is -3, lambda 2 is, if I set that equal to 0, positive 2. If your lambda 1 is somebody else's lambda 2, it doesn't really matter, okay? And yeah, just to point out, remember how I said for this same matrix, we saw that one of our eigenvalues was 2, right? That's what we got. I'm using the same matrix. So that's it right here. That's showing where that 2 came from. And now what we have to do is find the corresponding eigenvectors. I'll put each lambda has a corresponding eigenvector. And you have to find them one by one. So here, let's start with lambda 1 is equal to -3. And this is where I have, at least for me, an important question for you. There are two competing techniques for finding the eigenvector. And I kind of feel strongly about how to do this, at least in terms of helping you to understand what's going on. Okay. One of the techniques for finding the eigenvectors is to take this eigenvalue and put it right back into here and set that equal to 0. Does anybody, is that what she did in class? That's why I wanted to go to class today, but I couldn't. Because she did it that way on the pre-recorded videos. Good. Okay, good. That's, I'm seeing a no here. Because the way I recommend doing it, and it sounds like maybe she switched, is to use the definition. What, because I want my students to know what an eigenvalue is. I've had many students over the years say, I know how to find eigenvalues and eigenvectors, Grant, but I have no idea what it is. The whole idea of an eigenvalue is if we take our matrix times a special vector, this is what we're looking for. V1 is the eigenvector that corresponds to lambda 1. That we're just going to get our eigenvalue times that vector. In other words, if we take our original matrix A, 3, 6, -1, -4, times, okay, again, V1's what we're looking for. So we don't know what that is. So we'll just call that either X and Y or X1, X2. We are going to get our eigenvalue, which was -3 times X1, X2. So does this look more like how she did it? Yippee. Okay, good, good, good. That's good. Okay, so then, because, okay, just to follow up with what I said, I want people to know what an eigenvalue is and why it's important. Just comparing sides of the equation, do you see what the advantage of an eigenvalue is? If this is an equation, doesn't that mean this entire matrix of 4 numbers can essentially be treated as just one single number? Do you see that? If this equation is true, I could replace all 4 of those numbers with just a single number because they both should be equal to each other. And we're going to see how we can take advantage of that fact of replacing a matrix with just a number to be able to do some really cool things. So that's why it's really cool, eigenvalues. Anyhow, to find out what these vectors are, let's just multiply this out. Since this is an equation, the top row, 3x1 plus 6x2, since I multiplied the top row times the column, that should equal, okay, this, if I put that in, that would be -3x1. And what I'm looking for here is a relationship between x1 and x2. And just by writing this equation down, I already see what I can do. So if I take this equation and I subtract x1 over to the other side, 6x1 is equal to 6x2 is equal to -6x1, divide by 6. This is what I was looking for. I was looking, when I say a relationship, I mean an equation that links x2 to x1. Because what this tells me is whatever my eigenvector is, which is what I'm looking for, right? I'm looking for x1 and x2. It tells me that x2 needs to be the negative of whatever I pick for x1. And so then the idea is I want to choose something. What I would do is choose x1 to be some number. For example, if I let x1 be 1, then what would x2 be? x2 would be the negative of 1. It's going to be -1. This is an eigenvector. Now, before I go any further, I need to make sure that everybody understands is cool with this. Because you might say, Grant, well, why did you choose 1? Because it's an easy number, right? It's an easy number to. What if someone had chosen, so I'm going to put or, what if someone had chosen 2 for x1? Well, then what would have x2 have been? It would have been -2. That's fine too. Or what if someone had chosen -1 for x1? -1 for x1, well, then the negative of negative x1, x2 would have been 1. All of these are valid eigenvectors because they satisfy this equation. And I want everybody to know that because it's sometimes funny. I mean, back when we were in person, of course, when I'd show up to my office hours, oftentimes I'd have people like, really, really, fired up and everything. And they'd say, Grant, can you settle this argument? We're finding eigenvectors and I got this and my friend got this. Who's wrong? And it's always kind of fun. I get to say, nobody's wrong. You're both right. But they're always bothered by that, right? Because they look different. But it all comes down to, as long as they satisfy this equation, they are valid. And then the other note I need to make about this is what would happen if I chose x1 to be 0? If x1 was 0, that means x2 is automatically 0, right? Yes, it solves this inequality, but that's not an interesting vector, right? 0, 0 doesn't go anywhere. So we try not to do that, right? You wouldn't want to have 0, 0 as your answer. One other comment, okay, because there's a lot of stuff here that would. Did you notice that all I did was write out the first row times the column, set it equal to the top number, and that's all I needed? Notice I never did multiply out the bottom row. What would have happened if I had done that is it would have given me the same information. You can probably see it. Check it out. If I'd multiplied the bottom row, I would have had -x1 plus 4x2. That would have equaled the bottom number, -3x2. And this was a -4. Sorry, this is a minus. Okay, this was a minus. And if I added 4 over here, I would have had -x1 equals x2, which basically says the same thing. It does say the same thing, right? I would have gotten the same information. So usually, not always, but usually, all you have to do is write out one row times the column, set it equal to the top number, and that's all you really need to bother with. Now, there was another eigenvalue. So we've got the eigenvalue and the eigenvector. Let's do the one for lambda equals 2. So again, it's matrix times eigenvector. We'll call this V2 this time, is equal to lambda 2 times V2. 3, 6, -1, -4 times some vector that I'm trying to figure out equals 2 times that vector. If I multiply out the first row times the column, 3x1 plus 6x2 would have to equal the top number, 2x1. And let's see, I'm seeing here if I subtract 3x2 over here, I have 6x2 is equal to -x1, which means x1 is equal to -6x2. It doesn't matter which one you solve for. Like I could have solved for x2 and said it was -16x1, either one, it doesn't really matter. But I just need to solve for one of them. And then choose a number. Now, in this case, what I would do is, since x1 is -6 times x2, I would choose a number for x2. Now, if I choose 0, then this is going to be 0. I don't want that. So just pick the nice, just like I did in the last one. Why don't we choose x2 to be 1? because if x2 is 1, then clearly x1 would be negative 6 times 1, which is negative 6. Okay. Let's see if we can fit in at least one more here. I'll practice. So this is a new matrix, and the directions here would be find the eigenvalues and eigenvectors. This kind of math, by the way, eigenvalues and eigenvectors, if you've got friends in the 21 series, which is supposed to be the math series for the smarty people, right? Well, not, I shouldn't say that. You're also, you know what I mean? The math, science, engineering, right? It's supposed to be thought of as the most difficult math. It isn't really. I'd say the 17 series is more difficult than the 21 series. They're not going to be able to help you with this because they don't touch eigenvalues and eigenvectors. This is like a 22A subject, which is for math and engineering majors. That's like their 5th quarter of calculus before they start talking about eigenvalues and eigenvectors. So yeah, you won't get any help from them unless they're in their 2nd year or something like that. So, I would say this is a kind of a good opportunity, in 17B to like either impress your friends or maybe your parents. Oh, what are you studying? Oh, what are you studying in math? Oh, we're just doing, regular eigenvalues and eigenvectors, that kind of stuff, they'd be like, what? Einstein values? What are you talking about? Sounds so fancy, right? Okay, so this is what I mean. We're going to go straight to find your eigenvalues. Yes, it's the determinant of A minus lambda times I, but it's going to boil down to just being minus lambda on the main diagonals, and the off diagonals stay the same. Take that determinant, set it equal to 0. It's time to flex. That's right. That's right, Bella. You're going to blow their mind. That's right. Okay, so we have 2 minus lambda, 3 minus lambda, minus the off diagonal is 6. Foil this out, I get lambda squared. And you can sometimes go straight to it if you just do some math in your head. I'm going to have minus 2 lambda minus 3 lambda. So that's minus 5 lambda. And then I'm going to have 6 here, but then I'm going to subtract 6, right? 6 minus 6 is going to be, so this is just going to be lambda squared minus 5 lambda equals 0. So here I can solve for my lambdas just by factoring it out. I get either lambda equals 0 or lambda equals 5 as my 2 eigenvalues. So now to find the eigenvectors, it again doesn't matter which one you call which, so we'll just say lambda 1 is 0. Matrix times eigenvector equals lambda times eigenvector. So let's see what happens here. I get 2x1 plus 6x2 has to equal 0, right? 0 times x1 is just 0. And that I can do something with that. I could solve for either one here. What if I go 6x2 is equal to negative 2x1? So x2 is equal to negative 2/6 or negative 1/3 x1. So as far as the choosing goes, hopefully I've convinced you, you can choose number whatever you want, although you probably wouldn't want to choose 0 because you'll end up with 0, 0. Now, what I've done on the past ones is I chose 1. If I choose x1 to be 1, then that's going to make x2 negative 1/3. Totally fine. That's a valid eigenvector. But for the math we're going to be doing later on, I was going to say probably more in 17C, it's just going to be easier if we can avoid fractions in our eigenvector. So other than choosing 1, because you get to choose any number you want, right? You have some freedoms here. What might be a better number to choose for x1 so that when I solve for x2, I don't get a fraction? Yes, I would say either of those. I see 3 or negative 3. That's fine. Either one will work. I'm going to go ahead and choose positive 3, but negative 3 would work fine as well. So if I choose x1 to be 3, then x2 is negative 1/3 times 3 is going to be negative 1. If you had chosen negative 3 here, this would have been positive 1, right? Negative 3, positive 1. Either one of those would have worked. All right, try the second one. Find your eigenvector for lambda equals 5. So for mine, what I did is I solved for x2. I end up getting x2 as 1/2 x1. So kind of the same idea here. If I want to avoid fractions, what I would choose is x1 to be 2, and therefore x2 is going to be 1. That's what I would choose. But as we have acknowledged, there's more than one option there. One interesting thing that can happen as far as this goes, I need to show you, let me see if I can get through one more example here, because there's a situation that will come up when you're doing this method that you should know how to handle here. So this matrix A is 3, 1, 0, 4. So if I do my determinant of 3 minus lambda, 1, 0, 4 minus lambda, I end up just getting this times this, which is 3 minus lambda times 4 minus lambda minus 0 equals 0. And so if you think about it, unlike the last ones, there's no need to FOIL this out. It's all ready to go, right? If 3 minus lambda times 4 minus lambda equals 0, I can quickly spot my lambdas. My lambdas are going to be 3 and 4. And there is, I think this is discussed in the book, in that you can probably see that if if this one or this entry right here is 0, if one or both of them are 0, it's always gonna play out like this, where this would end up being 0, and you can just read off your eigenvalues, which are just going to be these numbers, right? So we might as well write it down. It's kind of a shortcut. So if one or both of your off diagonal entries is 0, then I guess we could say the main diagonal entries are your eigenvalues. The main diags are your lambdas. That's what we've got going on right here. And it doesn't take much work to do this, but if you see it, you might say, oh, and it's valid. I'm pretty sure that's written in the book. So if you get a matrix like this, you could just go right away. I can see my eigenvalues are 3 and 4, and then just go straight into your eigenvectors. Could be a little time saver on a test, on a short test. Oh, wait, we're done with short tests. On a quiz or a final. Okay, so then I'm pretty sure for one of these, I hope that I picked the right one. The thing that I wanted to show you comes up here. So let's start with lambda equals 3. So if I write this out, I get 3x1 plus 1x2 has to equal 3x1. And if that's the case, these two cancel out, and what it tells me is x2 has to be 0 if those cancel out. But notice here, it doesn't tell me anything about what x1 can be, right? It just tells me x2 needs to be 0. Now I said, I'm only been multiplying the first row. Look even if you go to the second multiplication, if you do 0x1 plus 4x2 equals 3x2, that's gone. When you think about it, the only number where 4 times x2 could equal 3 times x2 is also if x2 is equal to 0. Okay. So here's how you handle that. If either one of these tells you that one of them has to be 0, but it doesn't tell you anything about the other variable, here's what it means. x1 can be any number at all. x1 can be any number at all. So you know what number I would choose. If I'm allowed to pick, and I don't want to pick, if x2 has to be 0, right? Because my v1 here, what I know for sure is my bottom one needs to be 0. And if x1 can be any number, yeah, I don't want to pick 0 again. So what would be the next favorite number? How about just 1, huh? How about just 1? So your eigenvector in this case is 1, 0, or 2, 0, or 3, 0, 4, 0. But that would be the simplest eigenvector. I know I'm over time, but I guess since I started, I might as well finish this last one. So let's find the eigenvector for 4. And after a little while, I keep wanting to write this down because I really want to emphasize this idea that that's how we get an eigenvalue. But you can see you're basically just doing this same thing again. Only this time it's going to be equal to 4 times my eigenvector. And that gives me 3x1 plus x2 is equal to 4x1. If I subtract this over here, that gives me x2 is equal to x1. That's perfect. The simplest two numbers to choose that would satisfy that. What two numbers would you choose? Or what would your eigenvector be? Yeah, just choose 1 and 1, right? 1 and 1. Yeah. Okay. All right, so hopefully that helps between this class and what you did the hour before. It's a guaranteed question on the final or next quiz, be able to find the eigenvalues and eigenvectors from a matrix. I understand there's a kind of a different way of asking the same thing on your latest worksheet. So maybe think about, okay, if you're getting stuck on any kind of a conceptual question about an eigenvalue and an eigenvector, go back to your definition. This is the key to understanding eigenvalues and eigenvectors. So if you get stuck on some problems on your worksheets or homeworks, try to think about that. The answer might be hiding in that definition. All right, everyone. Yes.